This is our final video in chapter 14, and we're going to start here on section 14.7 talking about catalyst. So we're going to start with a homogeneous catalyst, but I do want to mention the properties of catalyst, or the characteristics of catalyst. And then we'll talk about this reaction that I have written up here. Catalyst, one, they increase the reaction rate by decreasing the activation energy. And so the reaction that we're looking at here is these are reactants, here are products, and when we add the catalyst, it decreases the activation energy from being very high down to being very low. In this example, this is the uncatalyzed reaction where we have hydrogen peroxide. It will decay to give us water and oxygen. If you have hydrogen peroxide in your house, it will be stable for probably several years, and then you can use it and it should still be effective. Sometimes people store it in the refrigerator, but whatever, it should be stable for a while. Usually it's in a dark bottle because sometimes light can cause it to decompose, but the rate of the reaction is very slow because it has a very high activation energy. However, if you throw a catalyst in there, it can go in just a couple seconds. So something that would be stable for years and years, you throw a little something in there and seconds and it's done. All right, so catalysts work by increasing the reaction rate. Catalysts change the mechanism by which the process occurs. So the mechanism by which this will go to this would be much different if you didn't have the catalyst present. But once you throw the catalyst in there, it sometimes will change it so it has more steps. It sometimes will change it so it has fewer steps. There's all kinds of things that can happen, but it will change the overall mechanism. Catalysts are not consumed in the course of the reaction. If you use a catalyst in one step, we saw this when we were looking at our rules for multi-step mechanisms. If you use a catalyst in one step, you have to consume that catalyst in a subsequent step. So, all right. Now, this particular reaction, here we've got H2O2 that decomposes into H2O plus oxygen. If you put in hydrobromic acid, HBr, what will happen is that the peroxide will oxidize that bromide ion. HBr is a strong acid, so it's a strong electrolyte, so you have bromide present. So it'll oxidize the bromide to give you bromine. And then, interestingly, bromine will also react with hydrogen peroxide. So Br2 will react with hydrogen peroxide, but here the bromine is going to get reduced. And when it gets reduced, you'll form oxygen plus HBr. So you'll notice that we started with HBr and that we ended up with HBr. So the reaction regenerated our catalyst. So HBr is acting as our catalyst. All right. So that kind of ticks off all the boxes for this. The only other point I want to mention about this slide is that this is a homogeneous catalyst example, meaning that everything is in the same phase. Our other possibilities include heterogeneous, which we're going to look at here in a couple of minutes, and enzymes, which are biological catalysts. As far as that reaction we just looked at, so here is the mechanism. This is what it looks like. And you can actually observe the intermediate because I'm going to point out hydrogen peroxide, colorless. HBr, colorless. Water, colorless. Oxygen, colorless. HBr, colors. Br2, brown. And so here it started off as colorless, but as the reaction proceeded, we get some brown material in there. That brown is the Br2, but then eventually that brown would get used up and we would be left, it would be left to look like this. So pretty cool. You don't always get a chance to observe the intermediate, but this intermediate is fairly stable, so it is possible to do. So now we want to look at something that's called a heterogeneous catalyst. So heterogeneous catalyst, the catalyst is in a different phase than the rest of the reaction. And the example that I'm going to show you, I'm not going to show you the details of the mechanism because the details of the mechanism are tricky and you're not ready for it. But I will show you the overall reaction. Typically, the absorption of the reactants onto or into the surface is usually going to be our rate determining step. But here is the overall reaction. If we take the compound ethylene and add hydrogen to it to produce ethane, we will find that if we put this into a regular flask and just kind of wait around for it to react, we could wait the rest of our lives and it would never react. And that's because the activation barrier for doing this is enormous. It is just enormous. However, if we take some metal, and the metal being palladium is usually the one we like to use, although there are a few other transition elements that we sometimes use. If we take palladium and absorb it onto activated carbon to give it a high surface area, we will find that this reaction will proceed pretty quickly and pretty reasonably. So the hydrogen will absorb onto the palladium, the ethylene will absorb onto the palladium, and then the hydrogen actually dissociates into hydrogen atoms, and then the hydrogen kind of migrates around and eventually runs into one of those carbons, and now you've got the hydrogen on the carbon, and then another one comes over and migrates, and then eventually you end up with ethane. Absolutely marvelous reaction. Another word for this is called hydrogenation. And you probably have heard of hydrogenation when you have looked at your snack food ingredients. Now, fortunately, you don't see this as much anymore because they're phasing it out. But if you ever look at your snack food and on the back it says partially hydrogenated vegetable oil or partially hydrogenated oil of some sort. What they do is that they take oils like vegetable oil. Vegetable oils have these carbon-carbon double bonds in them, and they add hydrogen to them to make them saturated. And you may think, oh, okay, well, they make they add hydrogen to them because that makes it healthier for you, right? And the answer to that is definitely not. They add hydrogen to them so that their snack foods will last longer. That's why they add hydrogen to them. In effect, it takes an unsaturated fat, an unsaturated oil, like a vegetable oil, and converts it into a saturated fat like animal fat. And that is not a good thing. And so, generally speaking, when you're eating snacks, you want to avoid things that have hydrogenated oils or partially hydrogenated oils. So this has been a little public service announcement. I hope that you are happy and healthier because of it. Okay, I will mention one last thing, is that the reverse of this reaction is used enormously in the petroleum industry. When you get crude oil, the crude oil mostly has carbon-carbon bonds that are single. Very few, if any, carbon-carbon double bonds. And typically, when you have crude oil, the oil is going to have a very, it's typically going to be kind of like a wax or sludge or something like that. And so part of the thing that they do when they process crude oil and convert it into gasoline is that they occasionally will come in and try to remove a couple of hydrogens. Well, one of the ways they can do this is the reverse process of hydrogenation. So by setting the conditions up correctly, you can force the reaction to go in the reverse direction, and you'll produce hydrogen plus a carbon-carbon double bond containing compound. And in doing so, this is the stuff they end up turning into gasoline, but the hydrogen, often they don't even have anywhere to put it. So sometimes they'll just take that hydrogen and they'll burn it at the top of their stack. So if you're ever looking for a very cheap source of hydrogen, just move right next to an oil refinery, and you can find those down on the coast. There's one right outside of Corpus Christi, right on the edge of Corpus Christi, and set up, and they will get you hydrogen for super cheap. All right. So At least that's how it used to work. They may have found a use for the hydrogen now. But anyway, that's hydrogenation, and you could do the dehydrogenation, and that's one of the steps they do in making gasoline. All right, finally, we're getting to the topic of enzymes, and enzymes are biological catalysts. Enzymes, in case you don't know, are just very big proteins that have a very specific job to do. So they are proteins, they're very, very large, and like I said, they are biological catalysts. Over here in this picture on the left, there is an example of a biological catalyst, catalase, which is an enzyme that is present in liver. Liver does all kinds of things and has lots of enzymes in it, and so one of the enzymes is this, so it's beef liver, and that catalase is really good at converting hydrogen peroxide into oxygen and water. And so it can do the same thing that the HBr did, but it does it very, very efficiently. So by adding a little bit of that catalyst, so if you smush up liver, this is kind of a gross experiment if you ever end up doing this, but if you ground up that liver, and so you get sort of a liver paste, it smells as good as you imagine. If you get a liver paste and you put a little bit of that paste into the hydrogen peroxide, you will find that it will bubble up very quickly and give off oxygen. So that is an example of a catalyst. Most of the time when you have a catalyst, catalyze a reaction, an enzyme, the enzyme and the substrate fit together much like a lock and key fit together. And so only that particular shaped substrate could possibly fit into that enzyme. Now you may have something that's a close match, and so you may get some competitive reactions that occur. They do this with some medicines that are like reuptake inhibitors that prevent neurotransmitters from being reabsorbed. But if you have a substrate that fits into an enzyme, that once it's in that condition, the structure of the enzyme makes it possible to do a reaction on that substrate that probably was impossible any other way. And so in this case, we're breaking apart that substrate into particles. There are lots and lots of enzymes in our body that are entirely designed to take chemicals that we consume and convert them into smaller chemicals that we can use. So this is the kind of process that occurs. And then over here, and like I said, it's a very specific, it's very hard to get a fake match. So it has to be a very specific size and shape molecule for this to work. And we'll find that they are, like I said, very, very specific. Down here, we've got a molecular model of what a particular enzyme looks like. And so you can see all the little spheres that are on there. Those are atoms. And so there's a little gap that's right there in this enzyme. And then our substrate can fit in that perfectly. And other size substrates probably would not fit in there perfectly. And so it would not be as effective on those other substrates. But that's kind of the idea of the lock and key mechanism. All right. And then here is my favorite page in all of chapter 14, which is the end.